Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's start today's talk. It's a great pleasure to introduce Nika Hachtalab. She's a graduate student at Carnegie Mellon University, advised by Avrim Blum and Ariel Prakacha. Nika works on learning theory, game theory, algorithms, and she already has some very exciting results. And today she will tell us about the case-center problem.
Thank you. I'm going to talk about symmetric and asymmetric case-center problem, and specifically how they behave under stability conditions. Let me first start by introducing my co-authors. This is a joint work with Nina Balcan and Colin White. I've tried very hard to include a lot of pictures and figures in this talk since it's a clustering talk, but I don't think any of them are going to look as good as these pictures do, but let's hope. Good, so we want to talk about case-center clustering. Case-center clustering is motivated by a very simple and natural question, which is if we want to, as an example, if we want to assign k locations in a city to fire stations, how can we do that? And where should we put these fire stations? But we should first think about what our goal is when we are putting fire stations. We really want to reduce the travel time for the worst location possible in the city. So if the worst location was going to be on fire, we want the closest fire station to be able to send a fire truck and resolve this issue very quickly. That is what case-center clustering is going to do. More formally, for a set of points S and a distance metric d, a k-clustering problem is a problem of choosing k of those points and assign them as centers, and then partitioning every point and assigning it to its closest center, and with the goal that to minimize the maximum possible radius in this sort of cover. Even more formally, we want to choose a set of centers. For the worst point in this set, we want to have the best distance being minimized. We are going to call this as a cost of the case-center clustering, and we'll refer to it as R star. As an example, let's have a bunch of points. We're going to assign the centers as the middle points. And the R star is really the cost of the largest edge here. The partition that's induced by this sort of assigning each point to its closest center is going to be the case-center clustering. Good. Distances are not always symmetric. They could be different in different directions. For example, when you're driving, you have one-way roads, so the distance to and from a location can be very different. We're going to consider case-center under two different notions of distance, one when it's symmetric and one when it's asymmetric. For the asymmetric setting, we still have some axioms about the distance, which is the distance of any point to itself is 0, and the directed triangle inequality holds. In addition, if you're in symmetric setting, you also have that for any point, any 2 points, the distance in either directions are the same. Our objective stays the same. We want to be able to minimize the distance from the center to the points. So this direction we care about, the backward direction we don't. It really doesn't matter. You could switch this as long as we stick with a consistent notion. Everything is good. So for this talk, we're going to stick with distance from the center to the points. There are well-known worst-case approximation results for both symmetric and asymmetric case-center. For the symmetric case-center, in 85, Gonzalez showed a tight two-approximation algorithm for the symmetric case-center. It's very simple, and you cannot do better than that. Any 2 minus epsilon approximation is going to be hard. For the asymmetric version, in 96 and then later in 2001, there was an approximation algorithm for O of log star of n. And if we need to remind ourselves what log star is, it's a super constant function. If you write n as a tower of powers of 2, the length of, or the height of this tower is log star n. So it's a very slowly growing function, but nevertheless, it's not constant. So there was an approximation algorithm for O of log star n. And the guess at that point was that this cannot be tight. It's not a very natural number to come up with. But as it turned out, it was tight. There was a matching lower bound for the asymmetric K-center of, again, O of log star n that was shown later. Question?
7 authors.
There are many authors on that paper, yes. This was a breakthrough result. Good. So in many situations, having a constant approximation, let alone a super constant approximation, is not very desirable. This is really a cost you're paying. So if you're paying double the cost, you might not be happy with that. But unfortunately, this existence of tight approximation guarantees stops us from going and getting better results. But the main problem here is that these tight results are really just for the worst case situation. And in many situations in real life, we are not always given this worst case scenario. A lot of times, it would be very pessimistic to assume that every day we are solving a worst case instance. So we want to go beyond this worst case analysis and focus on instances that can naturally occur in real life. What does that mean? It means that we assume certain natural assumptions, natural in double quotes, and then we are hoping that under those assumptions we can get better results, hoping that either we can reduce these approximation guarantees or we can actually find the exact solution.
If there is a problem for which I say worst case makes sense, it's typically case center, no? But your first example where you just showed.
Yeah, so maybe when I show you the type of natural assumptions we make, you will see that it does make actually a lot of sense. So maybe I'll come back to this question in 2 slides or 3 slides. Good? OK, so one of the notions that we are going to assume here is called perturbation resilience. And what it tries to capture is that in real life, we make some mistakes. Things that we measure can be a little bit off, or there can be fluctuations in it. For example, in this case, the traffic on one day is higher than the other day. So the travel time changes from one day to another. And this small changes, small fluctuations in the measure, our hope is that it's not going to entirely change our solution. So if we decide to put the fire stations at one place, after 6 months, hopefully we are not going to come back and say, oh, the traffic has changed by like it's epsilon, and now we have to destroy all the fire stations we had and come back and put like k different fire stations somewhere else. So that is what perturbation resilience is trying to capture, that small fluctuations don't make a big difference. More formally, actually not more formally yet, perturbation resilience for most of this talk, I'm going to assume that small fluctuations don't change the solution at all. So not that they don't change it drastically, but they don't change it at all. I'll make it more robust at the end. And this implies some more structure. And the hope is that this more structure is going to help us find the exact solution. Let's look at this example. So what is a perturbation or fluctuations in the distance are going to look like something like this. And in this specific scenario, there's a lot of structure present, so the clustering doesn't change at all. So this instance would be perturbation resilient. More formally, perturbation resilient was introduced by Bilu and Linial in 2012. And what it says is that for an instance and a distance metric, it is alpha perturbation resilient if I blow up the distances by at most a multiplicative factor of alpha. So this is what that is. Then the clustering or the solution does not change at all. So that is being alpha perturbation resilient. One very natural implication of this result is that actually the optimal clustering is unique already. Because optimal clustering, you're not making any extra perturbation to it. So if there exist two optimal clusterings, one has to be different. The other thing is that to note, it's fine if the centers change. All we care about is that the partition does not change under the new distance metric. It's OK if the centers do change. Is there any question about perturbation resilience? OK. The next natural assumption that we want to, well, we are not introducing, that I want to mention here for this talk is called approximation stability. And what it captures is that if you are approximating the cost of a function, of a clustering in this situation, you're also approximating the membership or the partition itself. So if you move within the cost for a partition that has better cost, the partition is also closer in membership to the actual optimal solution. This was introduced by Balcan, Blum, and Gupta in 2009. And more formally, what it is that if we have an alpha approximation of the cost, which for K-center is alpha r star, we have an epsilon fraction of the points being different than the optimal. So that's alpha epsilon. A very simple result is that if you have an alpha 0 approximation stable instance, you have an alpha perturbation resilient instance. This is relatively simple. So what it means is that approximation stability is actually a stronger notion of stability than perturbation resilience. OK. So at this point, is there still some worry about this? Or it is something that we decide. It's an assumption that we make about well-behaving instances. So prior work about perturbation resilience and approximation stability. So Bilu and Linial introduced this for max cut problem. And they showed that for square root of n perturbation resilient, they can find the exact optimal solution. Abbasi, Blum, and Sheffet showed that for center-based clustering, which is k-center, k-median, k-means, and a bunch of other clustering notions, under 3 perturbation, they can find the optimal clustering. Balcan and Liang improved this to 1 plus root 2 perturbation resilience. Makarichev, Vijayaragavan, which is Kostia's paper, introduced that improved the max cut from Bilu and Linials, and also showed that for a min multi-way cut, under 4 perturbation, you can find the optimal solution. For approximation stability, Balcan, Blum, Gupta showed that for k-means and k-medians, and also min-sum, if you have a 1 plus delta approximation stable instance, then you can find the optimal result quickly. In this talk, I'm going to first improve on this notion, which is the 3 PR and 1 plus square root of 2 PR. That's for the symmetric case. I'm going to show that for K-center, a 2 PR, 2 perturbation resilience is enough. On the other hand, for asymmetric, I'm going to show that if you have 3 perturbation resilience, you can find the exact optimal solution. And if you have 2 approximation stability, you can also find the exact solution. We also show that, but I'm not going to go through it in this talk as much, that both of these are tight. So anything under 2 perturbation resilience or 2 approximation stability for K-center, both symmetric and asymmetric, stays hard. Finding the optimal solution stays hard. To put into perspective what we're going to show, remember that before we have any stability assumptions, if we don't have any stability assumptions, I said that there is a tight 2 approximation for K-center and a tight log star n for asymmetric version of it. Under stability, the story changes a lot. We have the same 2 PR, the 2 perturbation, so we can find the exact solution under 2 perturbation. But for the asymmetric, perturbation resilience changes the story a lot. All of a sudden, from that log star n, we can go down to a constant alpha. And that's pretty cool. For approximation stability, that even goes farther. And in fact, And in fact, for both K-center and asymmetric K-center, we will have two approximation stability, which is, for this case, is pretty trivial. For asymmetric, not so much. So it's really interesting to see that under these stability assumptions, without them, two different problems could be very different in terms of difficulty. And with them, they could look very similar. Good. So I want to talk about the asymmetric version under perturbation resilience. One of the challenges when you're working with asymmetric clustering in general is that there are points that are their distance in the two different directions are very different. This is especially a problem when a point is much closer to a center of a different cluster, so this, then, oh, sorry, this is just showing that the two versions are different. A point is much closer to a center of different cluster than its own center. The problem here would be that if I draw a ball of radius r around each point, a point might not capture any of its own points in the same cluster. So these points are not really good. We don't want to deal with them, or we want to sort of filter them and not worry about them too much for now. I'm going to introduce a set called symmetrized set, which captures this notion. It's going to include points that their forward and backward distances are almost the same to some threshold r star. Formally, a point P is put in a symmetrized set if for all the other points, if that other point to P has distance less than r star, P also has distance less than r star to Q. Or even more formally, if this statement holds. If Q to P is smaller than r star, this implies that P to Q is also less than r star. So this means that in two directions, they are both under r star. Let's look at an example of this. So I'm going to put the definition of A up there, but if there's any question about it, please let me know, and I'll explain that. Let's look at this example. So for the maroon point, the only other point that we have in this set is a point that has a distance 2r to it. So for P equal to the maroon point and Q equal to the beige point, this is always false, because there is no point that has a distance of less than r star to P. So because the premise is false, this statement is always true. And our maroon point, is in the set A. For the beige point, however, we have a distance of r star going into it, but we have a distance of 2r star coming out. So that's not good. So that point is not going to be in the set A. One more example. We have, for the maroon point, we have a distance of r star going in, and again, a distance of 2r star coming out, even though they're from two different clusters. And again, that's not good. So that's not going to be in set A either. So I just defined the set A. Set A has symmetrized points in it. So it would be nice if set A is not empty, because if it's empty, what I did was completely useless. So I'm going to tell you about three properties of set A. And these three properties hold if we have three perturbation resilience. The first property is that all of the centers are in set A. And this is really nice. At least one point, and the most important point of each cluster, which is the center, is going to be in the set A. The second point is that if I only look at set A, 2 points are within the distance r star from each other, then they both belong to the same optimal cluster. Note that as long as we are in set A, if 2 points in one direction have distance of r star, in the other direction they also have distance of r star. So when we are considering set A, symmetry tells us that don't worry about the direction. For the third property, now looking outside of A, if I take a point outside of A, the point in A that has the closest distance to it and that point both belong to the same optimal cluster again. So these three properties show that there is a lot of structure present in the set A. Not only centers are part of it, and if you look at any R star threshold of the set A, the points belong to the same set. But also, even if you don't look in A and you're looking outside, the set A is going to guide you and tell you how you have to put these points in the same cluster. So if we have these three properties, then the algorithm is very natural. So our algorithm first starts by creating the set A. So the blue points are going to be in the set A. And then we are going to partition it based on R star, which means that any 2 points that are within R star away from each other, they're put in the same partition. Or you can think of it as draw these R star edges, and the graph, the connected components of these graphs are this graph is the partition. After doing that, for any point that was not in A, we're going to connect it to its closest point in A. The claim is that the clustering induced by this partition is the optimal clustering. I'm going to give you a 1-minute proof version of this by going through the algorithm one more time. We are going to create set A again. At this point, what do we know? A has all the centers, and that was by fact 1. So if fact 1 was correct, then A has all of the centers. Then we're going to partition set A based on R star. So at this point, we know a couple more properties. That because all the centers were in A, and a center, just the distance from a center to all of its points is R. So each center and the points in its own cluster are now put in the same partition. So that we know. We also know that, and that's just by the definition of the radius. We also know that no set has 2 points from 2 different clusters. Why is that? That's by fact 2. Fact 2 said that if you are within a distance of R star, then you're in part of the same cluster. So if I made this partition by R star, then by fact 2, I'm not mixing or merging any of the 2 different clusters together. Good. And what do I know at the end? I know that I connected each point to its corresponding closest point in A, which also has to belong to the same cluster by fact 3. So if facts 1, 2, 3 hold, then this algorithm is correct.
So even if facts 1 and 3 held, then you would have still got the unique cluster. I mean, where are you using the
No, because the point P for the second part. So I don't have an example here, but let's assume that there was a point here, that its closest point was this guy, or was a point that was not the center itself. Actually, this is a pretty good example. Yeah, this guy closest point is this guy. That's not the center. So if I don't know that these two have to belong to the same set, then that's a problem. Especially because fact 3 is defined for outside of A, not inside of A. So you do need the 3 facts. So is the algorithm and the overall proof clear? Yeah?
So I missed one thing. How do you know R star?
Good. You don't need to know it. You can guess it. You're not in a Euclidean setting, right? You're in a setting where you have n points and you have n squared distances. Guess R star. It has to be one of the n squared distances, and run this. That's one way of doing it. So if you don't know the optimal, you can always guess it because you're in a very discrete setting.
Okay, and if I guess incorrectly, then I will get what, the wrong number of clusters, or what?
Yeah, you get the wrong number of clusters.
Necessarily.
Yes, because this is like monotonic in K.
I guess you go to the smallest guess where you get the right number of clusters.
Binary switch perhaps.
Yeah. Good. Okay, so I want to give you a proof of fact 1 and 2. And fact 3, we are going to ignore the proof.
So sorry, how did you find the centers?
The centers?
Yeah.
I'm not finding them. The centers,
The centers are not, you're saying they're not, it's just clusters, huh?
Exactly. So once you have the cluster, you can find the center. So I'm saying this partition is the optimal clustering, then find the centers given the partition. Good. Okay. So I'm going to give you a proof of fact 1 and 2. especially because it's going to use a perturbation. So I want you guys to get a feel of like how these perturbations are important. Fact 3 we'll ignore for now. OK, a useful lemma. This is, by definition, a useful lemma. That is, for any point, the distance of that point to a center that it's not its own is more than 2r star. I want to prove this. And once I prove this, fact 1 and 2 follow very quickly from it. Let's assume that's not the case. So we have a p and a q such that p to that center is 2r star. So reversing this. So we're assuming that there is a 2r star distance between p and the center. So the distance between that center and q is, by definition, r star. Therefore, the distance of p to q is at most 3r star. So the distance of p to any point in the cluster that it's not its own is now at most 3r star. I'm going to make a perturbation. This perturbation is going to increase all of the distances by multiplying it by 3, except exactly the distances between p and this set. It's going to increase it to up to a 3r star. Above that, we are not going to increase it. So this is going to look like kind of like this, but it's very hard to show it in plain. But what happens at this point, we know that in this new distance metric, the distance between p and any other point is still the same 3r star. So if I were to cluster this way, the cost of this clustering would be 3r star. And the cost of this clustering is no more than r star. So this is a 3r star approximation in that sense. It's not really approximation, but the cost of this clustering is 3r star in the new distance. Also, in the new distance, what I did, I increased all of the distances that were r star before to 3r star now. So there is no way that my previous clustering now has a cost that is smaller than 3r star. So if I were to cluster the way that it was before, that cost of that clustering is at least 3r star. So I have two clusterings that both have cost 3r star, or the other clustering is actually better than it. So the optimal clustering is not unique anymore. This would be a contradiction. So I created a perturbation resilience, and I created a perturbation, and I showed that the optimal clustering is not unique anymore. Good. So this is very simple. And now let's use this lemma, which says that your distance to any center that's not your own is more than 2r star, to prove fact 1 and 2. The definition of A there, if we need it. So we want to show that all of the centers are in set A. Consider one of the clusters and that center. For the points that are part of that cluster, we know that the center to cluster, by definition, has distance of r star. So no matter what the backward dimension is, the second part of this implication is always correct. So the center is naturally always in that set. Except if there was a point that was also not in the same cluster, but pointing to you with a distance of r star. But our lemma says that this just cannot happen, because the distance of such a point is at least 2r star. So any center always satisfies this implication, and any center, therefore, is always in set A. Fact 2 says that if you're in set A, and if you're within r star of each other, you're both in the same optimal clustering. Assume not. So we have a P and a Q, such that they're within distance of r star from each other, but they're in two different clusters. So then, starting from P, going to Q, I'm paying a distance of r star. What about starting from Q going to the center? Q is in the set A. Because it's in the set A, and because the center to Q has a distance of r star, the Q to center also has to have a distance of r star. So the distance that Q pays to go to the center is also at most r star. Given that, using triangle inequality, P to the other center is now at most 2r star, which contradicts the lemma. So these two facts follow very naturally from the lemma that we had. Are there any questions about this? Good. So this proves that if you have 3 perturbation resilience instances for asymmetric K-center, you can find the exact optimal solution with a very simple algorithm that I showed you. Let's go to the symmetric case. So for the symmetric case, what we have is that I claim that a 2 perturbation resilience is enough. And that's because there is extra structure in K-center, like symmetry, for example, that is going to help us. We are going to use an algorithm that was introduced by Balcan and Liang. When it was introduced, it was shown to have 1 plus root 2 perturbation resilience, to work for 1 plus root 2 perturbation resilience. We are going to show that for K-center, it does better. Only 2 perturbation resilience is enough for it. And I'll just give you an overview of why. There are 2 key properties when you have 2 perturbation resilience in symmetric instances. I'm not going to prove them to you, but I'll tell you what they are. The first one is that if you draw a ball of radius r star, of radius ri at the center, then you're capturing points from that cluster, and only from that cluster, which means that this is not an instance of this property that I'm telling you, because I drew an r star ball and I captured another point. But if there was a little bit more structure, which is that, then such an example satisfies the coverage property. Draw a ball of your radius, you're capturing the cluster and exactly the cluster. The second,
Sorry.
Ri is the radius of cluster I. Yeah, so if this is Ci and this is big Ci cluster I, Ri is the radius of that. The second property that we call weak center proximity is that each point is closer to its own center than any other point, which means that if I take P and take it to its own center, and I take it to another point in a different cluster, the red edge is always smaller than the blue edge. So these 2 properties I can show that hold for any 2 perturbation resilient instance of K-center. They don't necessarily hold for other center-based clusterings, actually. So if you have 2 perturbation resilience here for K-medians, for example, the coverage doesn't work. So this is using K-center very much, like using the structure that exists in K-center. Based on these 2 properties, there is a notion called a closure distance notion, which says that for any 2 sets, the linkage, the closure linkage distance between these 2 sets is defined as follows. I will choose one center, and I will draw a radius of r ball around it. 2 properties should hold. The first one is that this ball should capture both A and B. And the second property is that anything else that also it captures, including A, B, and more, should be closer to this center than to any other point outside of this ball. This already sounds very much like the 2 properties that I explained to you. And there is a reason. Otherwise, they wouldn't have come up with this notion of distance. Let's look at an example. I have a set AB. I want to see what their closure distance is. So I will pick a center, and I will draw a radius of r around it, whatever radius this is r. So do I have the properties or not? So A and B are definitely captured, so that's good. But there's a point where the red edge is bigger than the blue edge. So this cannot be r star. This cannot be the closure distance. So I have to go slightly farther. So now I go farther to capture that bad point. And now any point that is within here is closer to the center than any point outside of it. So this is going to be the closure distance of set A and B. Let's do one more example. I want to show you that if I take two subsets of the same cluster, and I make sure that one of them has the center of the cluster in there, then the closure distance of these two is at most Ri, which is the radius of that center. OK, so we have the sets A and B. If it's not clear, A and B are the bigger sets. I'm going to draw a ball of radius Ri at the center. And I'm going to show you that it has the desired properties. So it has the first property because we said by the coverage property, if I drew a ball of radius Ri, I capture exactly the cluster. So that's good. It has the first property. For the second property, let's assume that it doesn't have it. Then, well, actually, by the weak center proximity, by definition, you have to be closer to your own center, which happens to be the center of the optimal cluster, than to any points outside of your cluster. This is exactly what weak center proximity says. So if you have two subsets of the same cluster, and you make sure that Ci is in one of them, the closure distance of the two is at most Ri. Good. Now I'll tell you what closure distance algorithm actually does. It's a linkage-based algorithm. It's very simple. It starts, once you understand the definition of closure distance is very simple. It starts with all the points being laid down like that. And it's going to consider them each being in one set. And now it's going to merge any two sets that have the smallest closure linkage distance. So this is going to be an example of it. And it will continue. It won't stop at k. It will just build this tree until there is one cluster left. So this is the hierarchical clustering of this instance. But we want exactly k centers. So we are going to find the best pruning. And we do that by dynamic programming. What is a pruning? The pruning is that we'll cut this tree at some point. And this would be the clusters left for it. We're going to do that and find the best cost cluster of size k that's left. Another pruning could be this, and there are 3 clusters left at this point. So this algorithm works given one condition, and that is if I did not merge any 2 clusters that were incomplete together at some point. So I want, when I look at one cluster at this point, it's either a subset of an optimal cluster, or it has multiple complete clusters in it. It cannot merge half of one cluster with another half of another cluster. So if such a condition holds, then the algorithm works by intuition. What I want to tell you is why it makes sense that this condition also works. I'm not going to give you a real proof, but I'll give you an intuitive proof. Let's take the simpler case, which is we are taking 2 subsets from 2 different clusters. And I want to tell you that this is not going to merge. Like, this merge is not going to happen at any point in the algorithm. Why not? So A might have the center in it or might not have the center in it. If it does, then good. If it doesn't, let's pick another A prime that does have the center of Ci in it. By what I explained to you 2 slides ago, we know that the closure distance of these 2 is at most Ri. If you want to remember, it's because the coverage, the ball keeps all of the points, and by weak center proximity, nothing is closer to points outside than the center. So definitely for A prime and A, the closure distance is Ri. What about for A and B? OK, so let's see what the closure distance is. We'll pick one center. We'll draw the point, the ball. And now we look at the center that was in A. What happens? The center, it's definitely closer to its points in its own cluster than the points outside. This is by the coverage. We said if we draw a small ball, I only capture my points. So the center is closer to a point outside. So this cannot satisfy the closure linkage. So if I want the closure distance, I have to go even farther and capture the whole set A, which means that now I have to pay more than Ri. This was just an example of the proof. This is not a total proof because there are cases we didn't cover. There are cases like, so what if one of them is a complete cluster? This is a much more challenging situation. So I'm not going to cover it, but intuitively, just because the larger the cluster is, the larger is going to be the closure distance. And the properties that we had, weak center proximity, and the coverage is going to help us with that. So this shows us that we have 2 perturbation resilience is enough for K-center. We also have lower bounds. We said that there is no polynomial time algorithm for symmetric instances of any 2 minus epsilon approximation stable clustering. So let's remember that if we had alpha approximation stability, we had alpha perturbation resilience. So our lower bound is for the stronger notion of stability than perturbation resilience. So it implies perturbation resilience lower bound as well. It's also for symmetric. Any symmetric instance is asymmetric as well. So this result says that a bunch of our results are tight, which is the 2 perturbation resilience for symmetric that I just showed you, the 2 approximation stability for asymmetric that I didn't show you, but it's very similar to the 3 perturbation way. What is not known to be tight is the 3 perturbation resilience for asymmetric. It will be very interesting if we figure this out. But we don't know right now if the 3 perturbation, the algorithm we have, is tight or not. I said that perturbation resilience, we're considering this scenario that the fluctuations do not make any difference in the clustering. This is not a robust notion. So we want to work with a more robust notion of perturbation resilience, which we call, which is called alpha epsilon perturbation resilience, which means that alpha perturbation, you're allowed to change by an epsilon. A little bit of change in membership as long as you have alpha perturbations. In the paper, we showed that a 4 epsilon perturbation resilience for K-center is enough. And the nice thing is that actually single linkage will give you that. It's an elaborate proof. I think if you have like 6 epsilon, it's very trivial. But 4 epsilon it takes a little bit of time.
So your results somehow depend on.
So you need your clusters to be larger than like epsilon n, like 2 epsilon n or something like that. You need some largeness of clusters assumption. Actually, we have lower bounds that says if they're not large, then it's already difficult.
But you get the exact optimum.
Yes, you get the exact optimum. We have more results for the robust notions of approximation stability that I'm not going to mention. Let's go back and think a little bit about what we showed. We started working with these like natural stability notions, like approximation stability and perturbation resilience, where the hope when these notions were introduced was that if I have 1 plus epsilon stability or 1 plus epsilon perturbation resilience, then I can still find either approximate or exact solution. That was the hope. So our lower bound kind of was negative in that sense. Even though, so upper bound, we showed that, great, we can take a problem that doesn't have a constant approximation ratio and show that 3 perturbation is enough. This was a very strongly positive result. Our lower bound is somewhat negative. That says that even at 2 perturbation resilience or 2 approximation stability, there's simply not enough structure and to find the optimal. So that means that going back, we need to think, hopefully this won't happen for k-means and k-medians. K-center is much more sensitive to distances. So the hope is that this will not happen for K-center and for k-means and k-medians. But it would be very interesting to see if you can even get less than 1 plus root 2. That's the best known result for it right now. And if it happens for k-means or k-medians, or if not, in general for K-center, we do need a stronger notion of stability. What would be a reasonable notion? That's not assuming way too much.
So something should blow up as epsilon goes to 0, right? But I'm not quite sure what's going to blow up here. I mean, Because you're not supposed to know epsilon, right? Or you are.
So if you look at for example, 1 plus epsilon approximation stability result, the Balcan Blum-Gupta, the runtime is also in epsilon, and also the restrictions on the cluster size they have is based on epsilon. So there are definitely things that won't work when epsilon is 0.
So the algorithm has to know epsilon in that case?
I don't know about their case. I think they have multiple results, I don't know.
Okay.
Yeah, but generally the hope is that you want to be able to say, I mean, two perturbations is kind of a large perturbation. But 1 plus epsilon you can justify very easily. So that's sort of the hope, and this lower bound is somewhat negative because of that. So we do need, if we want to consider K-center, or even K-means and K-median, depending on what we get, is that what would be a more natural, stable stability result that's not assuming way too much. To conclude, it would be interesting to see how asymmetry and stability work in general. So we showed that for the asymmetric clustering objective, how things worked. But in general, there are other asymmetric clustering objectives, like what happens with asymmetric K-means or asymmetric K-medians. That would be interesting. It's also very interesting to see if the hardness that we showed, is it tight for also 3 perturbation asymmetric situations or not? Because there's a gap of 2 to 3 for perturbation resilience considering asymmetric. So it will be very interesting to see what that actual value is. And with that, I want to thank you. Are there any questions?
So I guess in this, your algorithms in some sense are using this property, right?
Which property?
That you are resilient under perturbation to some extent, because it's.
Yes.
So for example, is this true? Let's say, like this would be to say, right, how, okay, except not, you don't typically do it for K-center, but typically in many of these problems, one massive approximation algorithms are just you solve a mathematical programming relaxation, typically DLP, and try to round it. And can you say, for example, under your assumption of perturbation resistance, that you solve LP, actually the solution will be integral? Because intuitively the picture in mind is that these clusters are so far away from each other, right? So that you can, like your algorithm can easily find out, because they don't really interact, because if they interacted or they're close by, like one of the points changes, it would enter a different cluster. And you know the optimal solutions are not changing.
Yeah,
So
I'm not
LP should tell you what the right answer is. Or
I'm not sure. Let's see. I'll tell you the right answer. I'm not sure if I can guarantee that. The algorithm, for example, the closure distance algorithm is, like, given the properties, it's sort of a natural notion of distance. But if you don't know those properties, it doesn't seem like something very natural. So I'm not sure if it will imply anything nice about the LP solution. But the properties that I proved definitely, or showed, they only hold for 2 perturbation resilience or 3 perturbation for that situation. Because if you go, and they're tight, if you go below that value, those properties break. And in fact, we have a section in our paper that is trying to address, so for K-center, sure, we got down from 1 plus root 2 to 2. What about K-means and K-median? So we are trying, we noticed that these properties break. So we try to replace these properties assuming some additional things. So maybe that's sort of like a first step to moving beyond K-center and moving beyond 1 plus root 2 in future. But it's not very clear that, I don't know, I don't think it would be easy just to show that the LP is all of a sudden behaving nicely. Like, you have to analyze that separately, I think.
I agree with Moïse. I mean, one of the issues of these algorithms is that they are not very robust in a sense. So, for instance, you talked a little bit about this alpha epsilon resilience. I mean, that seems much more interesting.
It is.
But what you showed us is not alpha epsilon resilience.
That's true. So the alpha epsilon, the implication of it is much more interesting. I agree. The results are much less crisp. That's why I didn't show it to you. And
do we know how nice result? Like, do we know there must be a separation between alpha epsilon and alpha 0?
No, I don't. We don't know a separation for it. So the best result we have for K-center is what I have, which is the 4 epsilon. I guess we think you can do 3 epsilon, but I don't know.
Robust algorithms look like the
So
one shown?
the robust algorithm for the 4 epsilon is single linkage. It's
Okay.
yeah. So it's showing that there are properties that hold.
This,
With K. No,
closure distance
no,
or
no,
just
no.
natural?
Single linkage.
Okay.
With a stopping
But
condition.
we make assumptions that the clusters are large, right?
Yes. So that you have to do. If you don't, we have hardness results.
But I mean, it's a natural algorithm that people actually run, so that's kind of...
Yeah, that's nice.
That's a good thing.
That's a good,
Exactly.
That's a good thing, yeah.
We have other sort of linkage style algorithms that like single linkage plus some pre-processing or post-processing that also shows, I think, is interesting because it's a real algorithm.
Because I'll be very surprised if the LP is not integral, right? Because if these clusters are very far away, clearly the LP can't cheat. It has to return you, right? Maybe distance 5, 10, I don't know what. But of course, the game is now to bring the constant down and make sure the LP still can't cheat, right? It's,
But in practice, would you solve the LP or would you actually run something like single linkage?
The algorithm
Just like from
is
the
rather
time point of
fast.
view.
Probably you can implement such algorithm.
Yeah, these are like n squared at most. It
no,
depends
but
on
my
what-
point
feel
is that
like
point is that typically, like if this you would do if you have this instance, right? Is that what? Oh, now we're going into a bit more
Yeah, that's okay.
philosophy.
It's getting more
What
philosophical.
people can
Yeah.
see.
Do you think one could get kind of some kind of trade-offs between, if for example you cared not about the exact solution, but just said somehow trade-offs between
Yeah.
PPR stability or approximation stability and approximation?
So you can, we have one result of that form that you get a 2 approximation, assuming, I don't remember exactly which one it is, but yes, there's a setting that you don't get an exact, you get some approximation for slightly better perturbation resilience style. So you can definitely do that. Our hardness results, of course, don't cover that, so I think it would be doable. I don't know of a nice connection between them, though. That would be cool, too. Yeah.
More questions? Then let's thank the speaker again.